Hi, and welcome to this quick review for Chemistry Chapter 2. Now, here we talk about the basic idea of what is matter. As you know, occupies space, has mass, came from God, who was created out of nothing. And if we look at how matter is organized into mixtures and pure substances, now there are differences between the two. But before we go there, we talk about physical properties and chemical properties. Now, if you think about physical properties, we're looking at those things we can measure without changing the material into something else. So we can look at things like color, taste, the texture, smooth or rough, and what physical state does it exist in, like a solid, a liquid, or a gas. But we can also talk about other things like density, for example. And that's quite possible you can get a density problem where density is mass over volume. Okay, we can also talk about malleability. How can a metal be shaped? Okay, that would be kind of important. Ductility is describing how easily the materials can be drawn into pretty thin wires. Okay, conductivity is how well does the material transfer heat or electricity between the particles. If you grab something that's very hot and it transfers to you, guess what? You are a fantastic conductor of heat. On the other end, if you take a hot pad and you put it on a hot object so you can bring it out of the oven and onto the table, and you're not receiving all that heat, that hot pad that you have is not a very good conductor of heat, which is actually a good thing. I skipped one. We got to talk about very fast. Particles. You guys should know this. Moving on. Chemical properties. Now, again, this is the idea of we do change the substance from one thing into another. So how does the matter react when you have other materials combined together, like concrete with water being a hard substance? What happens to the material? How does it change when you add enough energy, think heat, to it? Physical change and chemical change. The way to tell, if you start with item A and you end with item A, folding paper, cutting up aluminum foil, chopping wood, okay? All those are examples of physical change. When we look at a chemical change, you start with A and you end with B. So burning wood, burning paper, okay, those are examples of chemical changes. Lighting gasoline on fire, that's a chemical change because you're no longer going to have gasoline when the fire dies out. It's now completely different. So now we've looked at physical properties and chemical properties. We can look at pure substance, and we said it's consisting of only one type of matter. Now we keep that in mind. But we also have the mixture. And again, materials that can be separated into two or more pure substances by physical change, like that solid here. But there's two kinds of mixtures. There's heterogeneous and homogeneous. Heterogeneous, you have the parts that you can see, and they do settle out because of gravity, like that Paul Newman salad dressing there. We call that a suspension. Homogeneous, on the other hand, is a solution. Okay, it's a uniform mixture of two or more pure substances. So in other words, we have got things that are spread out evenly. That's what we mean by uniform. When we look at pure substances, as we move from solutions, pure substances, we have elements and compounds. Elements are made up of one kind of atom, like silver, oxygen, gold. Water is not an element. Water is a compound. Because a compound, you have two or more atoms there. The thing is that those compounds, it could be the same element, it could be different. So compounds could be elements, but compounds can also take into account different elements, like hydrogen plus oxygen, you have water. Carbon plus oxygen, you get carbon dioxide. Okay, so we talked about that. Atoms, again, those are the smallest piece of an element that's still the element. and it's made up of protons, neutrons, electrons. An ion is an atom that has a plus or minus charge to it. Now, elements do now occur naturally in three categories. They could be by themselves, monatomic. They could hook up with each other, like diatomic, or they could combine with more than two, which is polyatomic. And molecules, atoms bonded together. Boom. Okay? Now, the molecules themselves could be atoms of the same element or atoms of different elements. So now we look at each element has its own chemical symbol. It's one or two letters. First letter will always be capitalized. The second letter will always be lowercase. You can see the example, boron and calcium. Okay, so compounds, you got molecules from two or more different elements that have been chemically bonded together. Now the formula tells us the number of atoms of each element that's present. Okay? The subscript is telling us how many atoms of that particular element is in the formula. So we look here at this example, Fe2O3, and you notice there's 2 irons and there's 3 oxygens in there. It's very obvious. Now we do have coefficients, which tells us how many of these Fe2O3s we have running loose. These are great, this is a great test question. I give you a formula and I ask you, hey, how many oxygen atoms are there? So energy and matter. If we look at energy, ability to do work, okay? And we got 6 common forms of energy, like mechanical. This is where the words kinetic and potential come in. Kinetic is movement, energy. Okay, we have thermal energy, think heat energy. Acoustic is sound energy. Wah, 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 wah. Electromagnetic energy, think radio waves, television waves, X-rays, the rays from the sun, okay, microwaves. All those are examples of electromagnetic. There's chemical, like burning the gas, and of course nuclear energy. So, in looking at energy in chemistry, energy moves around and it changes. And that's where thermodynamics comes in. That's a separate branch in the sciences, in chemistry and physics. The first law of thermodynamics is there's 2 laws we're going to worry about here. One, energy can't be created or destroyed. Now, it can be changed from one form to another. We can take electrical energy and change that to sound energy. Think your cell phone. Think about that. Now, entropy measures the dispersal of the energy. Remember, dispersal is the scattering, spreading out. And every natural process goes toward the highest entropy with the minimal amount of energy. What does that mean? Things tend to go into disorder. As they go into disorder, you also have less energy. You burn gasoline in the car, exhaust comes out. You have molecules that are broken down, which means less order, but you also have less energy in there, because while the exhaust is warm or hot in terms of temperature, that's it. That's all. We can't really use it anymore. Once we've burned the gasoline, that's it. We can't use it anymore. So that's entropy. In the second law of thermodynamics, we said again, all natural processes go to the highest entropy, minimum usable energy. So entropy naturally goes up. It increases. Like the ice cube going into water, as you can see there. The system is part of the universe that the scientists study. We set this boundaries as to what is the system. We can look at the cooling system of a car. We can look at the digestive system of the human being, the nervous system of the human being, the endocrine system of the human being, okay, the cardiovascular system of the human being. So those are examples of systems that we're isolating certain parts of the universe that we're studying, and we ignore everything else. Okay? The particle mode of matter, basically everything, all matter consists of tiny particles. Remember, particles, it's the nice code name for atoms and molecules. Diffusion are particles that spread apart. Think perfume in a room. Brownian motion, where objects move and collide randomly, which is true. All you have to do is on a sunny day, you're in a room, you're facing a window, you see the sunlight go through the window. Look at the dust. Look where it's going. Randomly. Kinetic energy. Hey, we mentioned it before. Right, everything is constantly moving. That's the thing about kinetic energy. So the joule is the unit of energy. That's basically it. Don't worry about the formula. But the joule is the unit of energy. So when we look at the internal energy of the object, it is the summation, that's that M that's turned on its side. It's all the potential and kinetic energy of the object's particles. But for us, typically, we look at temperature, the average kinetic energy of a system's particles. Again, if we take human body temperature of somebody and we used all the methods for taking the temperature, we're going to find we have different numbers. And that's true. Thermal energy, we talk about kinetic energy of an object's particles. Heat transfer. Hey, you know when heat energy, thermal energy, goes between two objects or substances? Cooking an egg. Going from the stove through the pan into the egg. Just like that. So heat is not the same as temperature. That's a pretty important idea. You can have the same temperature between two objects, but different amounts of heat. Remember, heat, it's a certain amount of energy. Temperature is the average amount. So that depends on the size of the object, the materials, and all that. Now, exothermic and endothermic, pretty important idea. Exothermic releases energy to the outside. Endothermic absorbs energy from the surroundings. How can we tell about this? Okay, pretty simply put, we look at the temperature change. Exothermic, temperature goes up. Endothermic, temperature goes down. That's it. Okay, so temperature scales we use in chemistry, the Celsius and the Kelvin. There is an absolute zero. At this point right now, it's impossible to reach absolute zero. We're getting close. And then that's the formula for Kelvin. Don't worry about the temperature for Fahrenheit. That's off to the right-hand side. Calories and kilocalories. Basically, a calorie is how much heat is needed to change the temperature of a gram of water 1 degree Celsius. A kilocalorie is 1,000 calories. A kilocalorie is 1,000 of those small calories, which is one big C calorie, which is what you see on the side of soda cans, cereal boxes, things like that. Last part, kinetic-molecular theory. What's going on with particles when they're arranged in different states of matter? In a solid, the attractive forces between particles is greater than the kinetic energy between the particles. That's why they're able to stay together. In a liquid, some of that attractive force is overcome. They move around a little bit, but they remain close to each other. Gas, that's it, man. There are no attractive forces. It's all, woo! Yeah, baby, we're going. Partay in the house, yo! Okay, moving on. Plasma is superheated. Super heated. Electrons are stripped away. You've got a positive ion. It is actually the most common state of matter in our visible universe. It's just not that common here on planet Earth. But our sun, yes. Oh, yes. All right. Common states of matter, you guys should know this. Condensation, vaporization, freezing. You guys should know this. This is middle school and elementary science, guys. Should know that. And with that, ladies and gentlemen, I pulled it off in 15 minutes. You now have a genuine review. Thank you.